So here's a picture of mom and a little fetus. And at this point, when the fetus is still attached by the umbilical cord, everything that goes into the fetus is really originating from mom. She controls all the nutrients and all the oxygen that goes into that baby. And with oxygen in mind, there are a couple of interesting ways that the baby, in this case, this little fetus on the right, has come up with to be able to get as much oxygen as possible from mom. Because remember, the fetus is trying to grow, and it wants to make sure all of its tissues that are growing and developing have enough oxygen. So there are a couple of tricks. And the first trick, and let me actually just draw it out for you, is simply looking at a single vial of blood. If we look at a single vial of blood from mom and compare it to a vial of blood from babies. Let me try to draw the vials about the same height and width. These are the two vials. If I was to take now, let's say, a little bit of mom's blood and spin it down, let's say in this little tube, and then do the exact same thing with the baby's blood, take some of baby's blood and spin it down, that spun blood, once it's spun down, would actually separate out into little parts, right? You'd have three different little layers, and this first layer would be something like this. This is called the plasma. The next layer right below it, remember there's a little layer of white blood cells and platelets, and below that, right here, is a layer of red blood cells. And remember, red blood cells are the ones that contain the hemoglobin. They're the ones that are going to move oxygen around. And in mom, the percent this red layer takes up is about 35%, meaning this whole thing would be 100%. Let's say this entire thing would be 100%. And of that, just over 1/3, or 35% exactly, is that bottom red layer. That's the red blood cell layer. So we would call this the hematocrit, right? So this is mom's hematocrit. And this is a very typical number for a pregnant woman. It varies depending on, whether you're a man or a woman and what age you are. But for a pregnant woman, 35% is a pretty reasonable number. Now going over here to the baby side, let's draw in what baby's blood probably looks like. The baby has a lot less of the blood taken up by plasma, so that layer is going to be smaller. And then the next layer, the white blood cell layer, that's a very small layer anyway, so that's not going to change much. And the final layer, the third layer, is the red blood cell layer. This layer takes up about, let's say, about 55%. So I hope I didn't kind of misdraw that, but that's about right, about 55%. So here, the hematocrit is much higher. Now what does that mean? If the hematocrit is higher in the baby, about 55%, then that means that the baby actually has more red blood cells going around in a given amount of volume of blood, and those red blood cells then can take up more oxygen, because that's really the part of blood that we care about when it comes to moving oxygen around. So that's one trick. In terms of tricks for getting more oxygen, simply having more of the red blood cells in a given volume of blood is kind of the amount of red blood cells is going to go up in the fetus. And that's kind of one trick. When I say trick, that's what I mean. So what's another trick or strategy, I guess that's another word, that the baby or the fetus can come up with to get more oxygen from mom? Well, if we think of the amount, you can also think of the type. And what I mean by that is thinking specifically about the type of hemoglobin. So we know that the adult hemoglobin has 4 units to it. So let me draw out the adult hemoglobin over here on the left. Let me just first write out adult hemoglobin. So HB for hemoglobin and A for adult. And I'll write adult over here just so we keep track of which is which. And there isn't one type of adult hemoglobin. There is a main one, which is the one I'm going to draw, but there are a few different types that adults have. The main one, as I said, is this one. Has a couple of alpha units. This is just a protein peptide that is in some conformation. We call it alpha. And a couple of beta units, and these are slightly different looking than the alpha ones. And there's a 2-to-2 ratio. So each hemoglobin has 4 units. And here you can see that you have 2 of each type. Now, on the fetus side, you actually have something a little different. So we also have over here hemoglobin, HB, this time F for fetus. And just as before, the fetus has a few different types of hemoglobins, but the main one is HbF. And actually, this one also shares that alpha unit and has two of them just as before. But instead of a beta unit, this one has what we call a gamma unit. And this is the Greek letter for gamma. Now oxygen is going to bind, and both of the hemoglobins, both the adult and the fetus, can bind 4 oxygens. Let me just draw in 4 oxygens here. You get the idea. Now inside of red blood cells there's a little molecule, and I'm actually just going to kind of sketch it out for you. And this molecule has 3 carbons. Let me just number the carbons, 1, 2, 3. And coming off of the 2 carbon, this one right here, is an oxygen. And coming off of that oxygen is a phosphate. And remember, phosphate has typically 5 bonds. So I'm just going to show you what this little molecule looks like. In fact, the exact same thing is happening off the 3 carbon. So this molecule that exists inside of red blood cells, it looks like this. Has a couple of phosphates. And coming off this number 1 is something like this. So this is a little molecule, and it's called, and you maybe even take a stab at trying to guess what it's called. It's called 2,3, kind of referring to this 2 and this 3. Because it's got 2 phospho, so diphosphoglycerate. So that's diphospho, and then glycerate just refers to this part right here. This is kind of the part that is being referred to when we say glycerate. So diphosphoglycerate. And 2,3-diphosphoglycerate, let me just fix that, is actually sometimes shortened down to 2,3-DPG, because people don't like to say the whole thing. So they'll say 2,3-DPG, and that's what this molecule is. So this molecule, 2,3-DPG, is inside of red blood cells, and it actually helps the red blood cell get rid of oxygen. And the way it does that, it actually is a tiny little molecule. I'll draw it, now that you know what the whole structure looks like, I'll draw it as a yellow dot. This is the same thing. Let's just make an equal sign. They equal the same thing. This little molecule will go and bind in the middle here. And it likes to bind to the beta subunits. Actually, the beta subunits are shaped so that this thing can bind very easily. And it sits kind of nicely between all 4 subunits, the betas and the alphas. And when it does that, it actually makes the conformation or the shape of the molecule change so that these little oxygens want to move off. So basically what it does is it makes it easier for the oxygen to be released from the hemoglobin. Now when this molecule comes over on this side, on the fetus side, and tries to bond, guess what happens? Well, these gamma subunits basically say, go away. Go away. They don't want to bind to this 2,3-DPG. They don't have the right shape for it. And so they basically want this little molecule to get lost. And so this molecule doesn't bind as easily to hemoglobin F. And as a result, those molecules of hemoglobin don't get rid of oxygen nearly as easily as the hemoglobin A does. Now, why would we even have a molecule like 2,3-DPG around? What would it be doing there? Well, interestingly, the levels of 2,3-DPG actually go up in situations where you actually have more need for oxygen. So let's say chronically you're without oxygen. So what would a situation like that be, where you're chronically without oxygen? Well, let's say you live, I don't know, at the top of the Himalayan mountains, and the altitude is so high, you've got a high altitude, that the air itself doesn't have a lot of oxygen in it. In that situation, your tissues are kind of always or chronically without oxygen. Now, another situation could be, let's say you have a lung disease. Let's say you have a lung problem or lung disease, and it's a chronic lung disease where you're always having difficulty, getting oxygen to the blood. Well, again, the tissues are really lacking in oxygen. So there, the red blood cells would make a lot of the 2,3-DPG. Or a final situation, maybe you're anemic. Maybe you don't have a lot of red blood cells circulating around the body. And if you're anemic, the tissues are not getting as much oxygen as they wish they would. And again, in this situation, you might have more 2,3-DPG. So 2,3-DPG, its basic job is to try to make sure that oxygen is let off of the hemoglobin, so that if you have tissue that really needs that oxygen, it's more easy to actually deliver that oxygen to that tissue. So going back to the tricks for the fetus, you can see the fetus has a different type of hemoglobin from the adult. So let me draw out a little curve, and you'll see what this difference ends up doing. So let me sketch out a curve. Let's just draw out a little graph here. This will be the partial pressure of oxygen on this axis, and this will be O2 or oxygen saturation, looking at how many of those spots on hemoglobin are taken up. So this will be going up that way. Now let's start out with mom's hemoglobin or adult hemoglobin. You know, it has a kind of an S shape because of the cooperativity that we've talked about in the past. So this will be hemoglobin adult type or hemoglobin A. Now, if I had, let's say, really high levels of 2,3-DPG, let me just draw out what that would look like. So let's say we had a situation where you had high levels of 2,3-DPG, and it could be because of one of these reasons. Maybe you live on a high mountain, or you have chronic lung disease, or you're always anemic. If you had one of these situations and your 2,3-DPG levels were really high or higher than usual, then what would happen to your curve, it would look like this. The curve for oxygen binding or oxygen saturation basically kind of shifts over to the right. So we call this a right shift because the whole thing looks like it's just kind of moved over a little bit. And now at any point, let's say I just choose a random point here and I choose the same point here. So this is the same partial pressure of oxygen, right, which is somewhere down here. Now for the same partial pressure of oxygen, my curve actually went down, meaning I have less oxygen bound to hemoglobin in the presence of this molecule. And that makes sense with what we just said because the molecule helps kick off of the oxygen. Now, what if you had an opposite situation? What if I actually drew out a curve like this? And this could be, let's say, a situation where you have low levels of 2,3-DPG. Well, with low levels of 2,3-DPG, you can see that this would make sense because now all of a sudden that molecule is not around. It's not doing anything to help get the oxygen off. So of course oxygen is going to stay bound to hemoglobin, and at the same partial pressure of oxygen, more of the hemoglobin will be bound by oxygen. Now think back to the idea of fetal hemoglobin. Remember, fetal hemoglobin, we said, has this gamma unit, and the gamma doesn't like 2,3-DPG, doesn't like to bind to it, and so it says get lost, go away. And so in a sense, the way I've drawn it for a low level of 2,3-DPG, I could just as well erase that and say, well, this is the situation in the fetus. The fetal hemoglobin is basically this curve, right? So this is kind of the hemoglobin F curve. If you just look at the curve, it looks like it's left shifted. But the real concept behind it is that it's because those hemoglobin molecules don't like to bind 2,3-DPG, and so of course it's going to go in the opposite direction of the blue curve. So looking at these two curves now, the white one and the red one, the white one represents mom, the red one represents baby, and the white one, if you want to look at a point where about half of the hemoglobin molecules are bound to oxygen, that might be right about there, meaning this is about halfway up to here. This is actually 50% of the way there. So 50% of the hemoglobin molecules are bound to oxygen when the pressure of oxygen, the partial pressure of oxygen, is about 27. And for the fetus, this same kind of point of reaching halfway saturation is reached when the partial pressure is about 20. So it's interesting, for a lower partial pressure of oxygen, the baby or the fetus is able to accomplish the same thing the adult can accomplish at only a higher amount of oxygen in the environment or in the blood. And these values are called P50s. So if you see P50, if you see that term, you can remember now that the hemoglobin F P50 is lower than the hemoglobin A P50. And that is, again, the actual number is 20 versus 27, or thereabout. So these are the two tricks then. One is the amount of hemoglobin or red blood cells in the fetus, and the other is the type. And hemoglobin F binds oxygen much more tightly and has a lower P50.